And as you would understand, having such a big package and certifying it, where the code comes both from the community, which is Apache, and from within our own company where we have developers, the source code is changing pretty frequently. And when we certify this package and say that this is the version that works with each other, different components such as streaming components, storage components, and the applications, when they work together, there are a multitude of errors that get produced. And when you are trying to finish the certification process, it becomes really difficult to identify which is the component which is giving you the most amount of trouble, which is the component which is producing the maximum number of errors, and are there common errors which are showing up in different test scenarios. And the scope of the problem was pretty huge when we started last year. And then we took bites at it, and now we are at a space where we'll show you the demo of what we did, and we'll talk about some of the benefits that we've achieved by applying machine learning in this context. When we began on a single node storage, which just had all the logs. We had a single node processing engine, and then from there, how we moved into Spark and what are the benefits of using, let's say, Livy, the job processor in between. We're going to talk of some aspects of that. And we'll leave some time for Q&A. If there are any questions, please do feel free to ask. So some of the basics. HDP is the big cumulative package which has 25 plus components, and we keep adding at least 2 or 3 components every year. All of these are Apache-based components, and a lot of community participation happens in that. If we add up the number of developers, that's pretty huge. The source code, like I mentioned earlier, it arrives from both the community and from internal folks, and the source code keeps changing pretty frequently. We have the mainline releases, which we try to do twice a year, and then we have on top of it the maintenance releases, which keep going out time and time again. In addition, there are hot fixes and there are backports to like really old versions. And it becomes very difficult for anybody or the whole QE team to have context of all the changes that are being done and to figure out what are the errors that they should be focused on some releases which are, let's say, feature bearing and have a lot more source code modification than some of the other maintenance releases. There are system tests which are written for each component, and there are hundreds of new tests added every release. The problem is that the more test cases that you add, the more failures you encounter, and that just keeps growing exponentially. With the limited number of people that we have and the number of use cases increasing, it was pretty obvious that just doing a manual effort would not suffice. So we started looking at this problem. We thought of what could be done. We started looking at logs, and then we derived some very interesting theoretical insights before we went ahead and applied those concepts or applied machine learning on those theoretical concepts. Now, typically we do a release when we say, okay, the system tests are above 95% on all, preferably at 100%, but in some cases we let go at about 97, 98%. That's a pretty high percentage to achieve. And I don't mean that we comment out test cases, we keep running them all. And the releases are done for both on-prem and for HDI and HTC, which is our cloud offering, and the HDI is the Microsoft thing, which is the HD initiatives. Now, just the magnitude of our problem, the system test cases that we have, they are organized as suites, and these suites we also call as splits inside the company, and these splits number at about 700. Now, what this 700 means is that these are unique sets of test cases which run on different components. None of them overlap with each other. Therefore, they are testing either a particular scenario or a particular component or a particular product. So these are non-overlapping test cases which are run. There are 700 of these. Several thousands of test cases in each of these splits. And one run for us is that once we have produced an HTTP build, then we say that, okay, go take these bits, create a cluster, and run your suite on top of it. So that's typically the process. Now, in one run, we may not pick all of these 700 splits, but we pick a significant number of those on a daily basis. The infrastructure that we have inside is based on Yarn. We've built our own cloud infrastructure using Yarn and the OpenStack infrastructure, which has been existing in the company for quite a bit. Like I mentioned, every split is run on its own cluster. And 700 of these 5-node plus clusters are created every day and torn down. And when you run for every suit, if you have, let's say, 2,000 test cases, then those 2,000 test cases are executing 2,000 different code paths, which is producing a huge amount of data in terms of system logs, error logs, application logs, and other, just the core bare metal or the cloud logs. Those are separate. We don't consider them. Test suites are run on each cluster and logs are collected, so we collect all the logs. And the total volume of the kind of logs that we produce on a daily basis is about anywhere between 1 and 1.5 terabytes. We also have a problem of storage of these. We don't want to store too much of that. And the reasons are very simple. If you have a fast-moving release which is feature-bearing, then you have a lot of code coming in. And the logs that you get on, let's say, day 0, versus the logs that you get on day 30, there'll be very little correlation between these logs. So there's not much point in storing all of it. What you would like to store, though, is the insight on top of it. And that is the process that we followed over here. Now, prior to introducing this whole machine learning and the Mool tool inside the company, everything was assessed manually. So component owners would have to go into each of the component logs, look at what those logs contain, figure out the exceptions, and then go back and report to their component owners that, look, here is a problem that exists in your component, why don't you go and fix it? And typically, in some cases, what we would find is that the same bug would get open into multiple stacks because the call would originate at an application level, let's say a Hive query, which then goes into a yarn application process, which then goes into Thales and then goes into HDFS to do something. Now, these components are related. So if in that case, your HDFS, if it was not set up properly, you had some kind of security problem, then you would have the same exception getting reported across components. And all the component owners would go and report the same exception, and all the component dev owners would then go and try to fix the same bug. And the problem was actually a setup problem. So duplication of these kind of errors was a very common scenario. We always had this problem. And this was going on day in and day out. So we decided on some objectives. One of the biggest objectives, or rather the primary objective of this whole Mool automated log analysis, was that we should be able to get to root cause analysis in a single click. Which means that if there are common exceptions which are occurring across components, then you should have the ability of clicking at one button, getting the root cause of it, filing a bug, and getting that fixed. And not just that, if there was a bug which was already open in one of your ticketing systems, then you go back and reopen that ticket. Or if there was a ticket which was closed, then you go and reopen that ticket saying that, look, this has record. So we wanted to automate this whole process. The second and the equally more important objective of this was that you had to recommend actions instead of just assisting search. So when you have these large amount of logs, one of the first things that people tend to do and companies tend to do is to enable search across all of these, easy search. So a lot of companies, they put it into log search, use ELK or something, and they assist in search. So you know the terms, you look for the exception, and then you try to split across a timeline and see where have these exceptions been created, and should they be reported as bugs or not. And we didn't want to do that. The other thing is that not everybody has expertise. So for example, if you looked at the Hadoop stack, it's pretty diverse. One part is storage, the other is streaming, the third is querying. Now, any component owner will find it very difficult to have expertise in all of these 3 areas or 4 areas, and then say with like a huge amount of, or 90% confidence that, look, this is the problem. So that was another objective. We wanted to create a systemic knowledge repository of errors and their associations. It is quite likely that when you have a multi-stack call, then probably the call or probably the code path which is causing all of these exceptions is a single one, and the rest will just follow. So we wanted to create that error hierarchy or graph as well. And like I mentioned, the integration with the downstream process lifecycle, the test analysis should be pretty easy, and the ticketing system integration. And by the way, the etymology of Mool is actually in Sanskrit, which means root, and we wanted to get to root cause analysis pretty quickly. So when we started looking at this, we looked at some of the other efforts which were done. One of the most significant ones which I found was one of the papers that was written by Wai-Ksie Lee at Uppsala, was automated log analysis using machine learning. And she wrote in her final conclusion in a very interesting paper that she put in is that the biggest limitation in our project is that it is hard to find experts to analyze the logs manually. Although the clustering algorithms do not need any feedback during learning, the evaluation of different models need to compare our prediction results with the true answers. But it is not possible to find experts to do manual log analysis in this project. And therefore, the evaluation is based on the test system verdicts. Now, this was kind of a very disappointing conclusion when we read this paper the first time in last August. But then the advantage that we had, on the contrary, was that we had a lot of people who had manual ability to go and verify whether our models were working or not. Because we already had a trained set of about 50 people in QE who could go and tell us that, look, your models are just not working. And we had a lot of those back and forth discussions as we kept going along. We discarded a lot of models as we developed them. So this kind of barrier did not exist for us in the company. And even since this was a complete tech product and a lot of devs also contributed into this, most of the times we were able to figure out that, yeah, your accuracy on this prediction is about 90%, and your root cause analysis that you found is correct. And so that kind of helped the whole process. Now, as is typical in any machine learning application processor or process, this is the same process that we followed. We had a feature extraction step which preceded the rest. We read through our logs, extracted the features that were most important for us. The interesting thing for us was that failures would not occur by themselves. Failures would be triggered because a test case was run somewhere. And therefore, if you split by, let's say, timestamp of start and timestamp of end of a particular suite, then you'd get to know all the errors that got produced in that time interval. And then what you had to figure out was that which components did they belong to, and what was the effect on let's say one error onto the other. Is there an association between these errors or not? So these two features were pretty important. What time did the tests start running, etc. And we'll cover that in a little bit more detail. The enrichment was with test execution time, like I mentioned, the start time and the end time. And every time that you looked at an exception, you would look at the stack trace and the message, and that would pretty much give you the origin component. And that was pretty helpful. Of course, we had to kind of go up the chain, look at all the stack traces that preceded, let's say, the RCA stack trace, and then go up the chain or come down and say, looks like these are the origin components that were affected. And the learning part was we first wanted to categorize the errors, because the number of errors that we were getting were huge, but they were hugely repetitive as well. So one of the first things that we thought of is that we need to identify unique errors which occur over a period of time and are repeated. Because if there is a code path which gets executed and that, let's say, it occurs in a component such as Uzi is not going to change too much. So you will pretty much receive the same exceptions time and time again, unless you see an equivalent source code modification on the other end. So we want to categorize these and keep it in our repository and use it for subsequent analysis as well. So that became our repository of all kinds of errors. And of course, the learning meant that we were doing RCA analysis. And every time that we would complete a run, we would go back and update our database into the meta store, as we call that, in updating the hierarchy of these errors. So which are the errors which actually cause the other errors, and what's basically the whole tree of that error. There's a little bit of algebra behind it. Like I mentioned, we have runs which contain multiple components, and every component has multiple splits. Each of these splits, they have multiple test cases in between. They have test case 1, 2, 3, and 4, and so on and so forth. On the right-hand side, you will see these errors. Now, these errors are E1, E2, E3, and E4, just for depiction. Now, it is possible that test case 1, when it was executed, caused error 1, 2, and 4. Test case 2 caused error 1 and 3, test case 3, E3 and E4, and test case 4, E1 and E4. Now, if you look at it, there is a commonality between the occurrence of E1 in multiple test cases. So if you do the converse relationship between errors and test cases, you would see that error 1 has occurred in test case 1, 2, and 4, and error 4 has occurred in test case 1 and test case 4. And you would always get a bounded statement, because the number of components which you've run can be determined by the test suite that you've run, because you know which components are you running it in. And if these errors or exceptions were generated in, if E1 to E4 or to En, EI 0 to N, was produced in any of those components, then you would know the origin component of that, because it would deliver a message and it would deliver a stack trace. So this kind of became the the founding equation for us, and we started at this point. And then we kept going from there. So that became the first step. Now, just a little more explanation on this. So if you look at the x-axis, it's basically the time graph, time t. T is 0, and at time t, your execution starts when you start getting the actual errors. And at time f, that execution is completed. So let's say that you get E1, E2, E3, which were produced by the running of TC1, TC2, and so on and so forth. Similarly, you ran the second suite also. You started at the same time. You started receiving errors at maybe a different time. But you then know that, okay, all of these errors have been produced in a certain time window, which you would then use to slice and collect all these errors which appeared in that time window. And similarly, so I and N, they started later, but they also produced these errors. So now what we do is we basically, so this is, by the way, a single cluster run. Now, which means that all these suites are basically running for a component. At this point in time, we are talking only one cluster. However, in our cases, what actually would happen is that you would running each of these test suites in multiple clusters. Now, which meant that the problem just got worse, because now you had to go and collect logs from all of these clusters which you just ended up running, bring them back, split them on timestamp, find the correlation as the first step, and then the second step, you would cluster them. And you would cluster them on the basis of timestamp. The first thing was deduplication, which is categorization of the errors themselves. And then you would know that, okay, even if you got, let's say, 10 million errors in the past 20,000 runs, you just have about 40,000 unique errors. And then out of those 40,000 unique errors, then you would cluster them on the basis of timestamp, which would then tell you, okay, looks like all of these guys, they got together. These were the other clusters that got formed. And in that cluster, then the objective becomes, okay, which is the one that actually caused the failure, which then becomes a secondary clustering or a time ordering problem inside that cluster of errors. Now, like I mentioned, if you have different suites on the top, if you look at the Hive suite or the Spark suite or the Uzi workflow, and typically what happens is, if you're running a Hive query, it goes through Hive server 2, then to Yarn, then to ADS, and then HDFS eventually, and then it produces a bunch of these errors. Whereas if you go to the second column, which is the Spark column, now you have Livy, Yarn, and HDFS, and those also go and produce, they may produce more errors, but there are some overlaps. So for example, it may go and produce E1, E2, and E3, in addition to producing E4, E5, and E6, which is the total list of it. Now, which means that common exceptions or common errors are being produced in different code path executions, because there is interrelation between the components themselves. So a Spark is also going to go and try to read HDFS because it tries to do something. Hive is also going to go and read on HDFS because before it allows you to run a query. And this was one important realization that we had. Now, the features that we ended up creating for test cases was basically, in our case, was name, the suite name, the start time, end time, and the status. And for the error features, we took stack trace. We did not take the whole stack trace, by the way. We actually took the exception, and then we took a few lines on top and a few lines on bottom, and this we kept adjusting till we got to the right place. What we also figured out was that above does not matter so much, because we'll never be able to walk up the whole source code tree and then say that, oh, look, the error was preceded by this call. That doesn't make sense, and it did not make sense for us. So we actually said, okay, stack trace plus, say, about 20, 25 lines. The message was important, but the problem is that when you have so much code coming in, it's always difficult to get the right message. And several of these exceptions are produced only to give a log, but they actually don't mean something. So for example, if you've got a condition in which if A is less than B, then you would also want to put an exception as just an error log saying that, oh, look, this condition was not satisfied. But it actually doesn't mean an error. So we have to find those and sift those out as well, because in code several times what we do is we just log an exception even though it doesn't really matter. the logging level is different or should have been more appropriate. And that is missing in a lot of our stack components. This is one of the samples of what data we end up getting. So on the left, you see that this is basically the data that we collect. It gives us the split ID, the component ID, and the run ID. And in terms of test, it tells us the name of the test case. It tells us that, okay, this belongs to split 19 when it is trying to check this and that. It belongs to some suite. And the status is 2, which in our case is a failure. And this was the time at which the test started, and this is the time at which it ended. The failure, if you look at the important section over there, is that it comes with a log. The log has a timestamp, and along with that is a message. And that message says that there is some problem in the Ranger admin REST client, and there was an error in getting policies. Now, this kind of setup error can typically destroy all your runs, because if you've not set up your policies correctly, then you're not going to be able to access your HDFS system or some other system, and that is going to cause a massive number of failures. So you might get about 500 failures for just one exception, and that was because somebody did not set it up properly. Now, so how did we build our system? So the system interactions are as follows. We have a data pipeline which at this point in time works in batch mode. We've not enabled event-based modes because frankly we've not seen enough benefits in trying to event every exception and trying to predict whether we understand the root cause of it immediately or not. What is really important for us is that we get enough data which we can then splice and then predict that, yeah, looks like this is the one. So post-factor works better for us. So we've not gone into eventing yet, although we intend to experiment with it significantly. The other important systems of data are basically your customer reports. So for example, in our case, a lot of customer reports, they get logged into Salesforce, so we want to read that. Source code modifications, we've already started testing. So if there is an error which we can attribute to a Git check-in, then that is really important and helpful for the quick turnaround on the fix. The historical error database is maintained. We already have that. We also plan to export this and try to put this in live systems and see what happens. And then there is the whole ticketing system which Dev and QE use, which in our case is Jira. Now, once you have data from the errors and you have data which comes from the other systems that exist inside the company, then you take them through a learning and modeling process. And then eventually you come up with the recommendations that you give to the QE analysts and the automated actions such as creating of tickets or resolving tickets or reopening tickets. So that is how we built the system. For the next sections, I'll just invite Gaurav to talk you through the application architecture, the deployment architecture, and then we'll do the demo.
Thanks, Rohit. I will talk about the application architecture, and then we will have a demo. So this whole application architecture has primarily 4 parts. First part is ingestion, where we collect the logs, parse them. We use grok parser to parse all the logs. And second part is error matching and categorization, so deduplication of the errors. So we have an error repository where we match all the errors to all the previously seen error and update the repository if we see any new error. After that, we have an RCA analysis and error hierarchy association. And then fourth part is based on the analysis, we have to take some actions, recommend proactive actions. So for stack trace, for error categorization, we use first we do two level of error categorization. First, we check for the exact identical match, and then second, we check for fuzzy match using Levenstein. So we use word level Levenstein instead of character level, and we have also weight Levenstein for matching the errors. For RCA association, we want to find root cause. For that, we use time slice and then cluster all the errors and try to find which error is the root cause for across the components. Then after all these analysis, we use those analysis to do actions like updating a Jira, creating if there's already Jira exists for that RCA, then update the Jira with the command that this has been seen in this run. If there's no Jira, then we can create a new one like this. Deployment architecture. So test cases runs in splits. So a split is a 5-node cluster. After the test case is completed, there's a log daemon that collects the log from each of the nodes and push it into an HDFS. After the log got pushed, then it triggers a Levy job. It triggers a Levy job that spawns a Spark job. So a Spark job is our core that do all the processing part. So what we have seen previously, this error categorization and RCA analysis, error hierarchy analysis is the part which is doing inside those jobs. So all the Spark jobs will read data from the HDFS and also read data from metadata store and provide a result which is written inside a metadata store. Then we have a front-end web application where we can see what's the status of the current run and what are the RCAs. And from the front end, we have an ability to reject the RCAs. So during the first attempt, we tried to find that error graphs. We try to find the error hierarchy. So suppose if we run a query from Hive view, it goes to a yarn, and then it spawns a yarn job, and that yarn job reads from a SDFS. If there's some permission error in the SDFS, it results in error in SDFS, then which in SDFS Hive also, and then in Hive view also. So we have all 3 errors for one query, and its root cause is the SDFS. So we try to find out this error hierarchy, that even because of the error in SDFS, we got an error in Hive, and then from the Hive error, we got error in Hive view logs. For that, we use time as a dimension, and we try to apply associative algorithm on top of it to find that hierarchy. But in the end, we find that it's not working properly. They have too many closed loops. This is mainly because of we have many errors that are not relevant to test cases. So across the Hadoop stack, there are many components that is producing those errors, but it's not related to the test failures. And then our second attempt is to find out the RCAs. So instead of finding the whole error hierarchy, we moved to finding the origin of the hierarchy, and that is simpler than finding the error hierarchy. It is also easy to validate, as the component owner will be knowing that this is the error that caused these test cases to fail. So it's easy to validate, easy to implement, and we can calculate accuracy. accuracy is higher than what we have got through the error hierarchy graphs. So RCA rejections. So our RCA algorithm gives us that these are the RCA which is causing so many test cases to fail, but it is not always correct. Sometimes we get multiple RCAs for single test, and sometimes that RCA what we are showing is not correct. So from the UI we have given that our algorithm is not working in this case, and so you can reject and the system can learn from that. Also, in the HDP stack, there are each component is generating some error, whether is it used by the test case, is it touched by the test case or not. So we have lot many errors which are not exactly contributing to the test case failure. For that, we try to implement, we try to prioritize some errors, and we try to prioritize some error and try to ignore some. So this error ignored, for this we use some statistics that this error is seen in so many times in in this run and also previously, so that we can safely ignore it or prioritize it if it's not seen much and it's present in every test failures. So RCA graph looks like this. Red, we will talk more about this in demo.
Okay, so this is basically the demo. 1 second. Sorry, I'll just play a video and then we can do a demo as well. So this is how the application looks like. This is the dashboard. Typically what happens is that the analysts, so there are two views which are important. The analysts actually come onto this dashboard, and the run IDs are the identifiers that analysts look for. They come and pick the run ID, and then there are two views that they may be interested in. If it is a component owner, then he's only going to look at the analysis of his own component. If he is like the complete, or if you are the manager or so-called the release manager, then you are more interested in looking at the RCAs, which means that you're looking across the stack. So the first thing that you would probably want to come and do over here is look for your old component or your run ID, and then start looking for results. Now, you search for it on the front end. You look at when was this run complete. You look at all the components that were run in this particular run ID, and then you select that. Once you select, this basically goes and creates the RCA graph for you at the beginning itself. So if you look at the cluster of failures, now the red dots, they basically indicate RCAs. The blue dots are basically the failures of all test cases, and these may be across components. And now the interesting point over here is that now there were like hundreds and hundreds of failures, but the actual RCAs were just about 17. So now when somebody is trying to analyze one of these RCAs and try to look at what's really going on, now you see that there is a stack trace which is available on the top, and then subsequently you have the different components in which you have failures. Now if you just take a look at the exception that's occurring, it says that Spinago authentication failed. which means that security was not set up properly, and that is causing failures in multiple components such as yarn, Taze, etc. And each of these components have multiple test cases failures inside it. So as soon as you click on that, you get into the details. So again, Livy session expired, and therefore it is causing failures in both Spark and Livy. So at the top, you can decide what component you want to analyze. So in this case, the analyst is picking Taze. And all the failures that were actually found in Taze was just because of a single problem, which was the Spinago problem. Now, which meant that the individual test case owners would not have to go to all of these places to look for their errors. They would just come, point to the RCA, either file a bug or let the automation subsequently take over, which is creation of tickets and stuff. Now, some of the other parts that Gaurav was talking about was basically about priority errors, ignored errors, and history. So we have a complete history of the last 5 months now, which is available. We have a list of priority errors, and the ones that are marked in blue are basically the ones, those are RCAs. Those are the ones that are actually causing failures. Now, the other thing that I talked about earlier was that inside the code itself, you have like a lot of failures, but those failures actually don't contribute to being the root cause. And those are just statistically, via decile formulas, we've just ignored them. And this has been like a continuous struggle for us. At what decile do we cut? Do we cut at 10, 20, 30, 40, or 70? 70, 75 has been working for us pretty okay. So these errors do occur, but they actually don't mean anything. These are like almost irrelevant. Some of the other things, so for example, you could click on this ignored error, click on the details, and look at all the other components in which the same error is occurring. So it just gives you a general overview of the things or the failures that occur. So I'll stop the demo as we are running out of time, but we can do a demo if we can do a detailed demo if there's more interest. I wanted to cover the stats, which are like really important. So the total runs that we've analyzed so far is 14,410, and the total splits are higher than 115,000, the number of times these splits were run. The total errors, the raw logs that we parsed, they were 120 million. But what was surprising was that the total number of unique errors was just about 45,000. And it was just the combination of these 45,000 errors that kept repeating itself. And this was like one of the biggest insights that we got. And the total test case failure over a period of time, it keeps growing, 170,000. And the errors that were related to these failed test cases were 592K, almost like 600,000. But if you looked at the uniqueness of it, it was still 45,000. So the amount of efficiency that we've been able to drive in this whole QE process has been significant. Some of the adoption challenges that I think we should talk about: QE analysts not being able to give us the insights in the first go, the system not giving them the right data, RCAs being identified incorrectly, log collection was partly complete, partly incomplete in some of the components in some of our automation frameworks, and that I think these cycles have to be gone through. There's no other way. Stable releases will give you fewer errors, and therefore RCA analysis will be weaker. Whereas fast-moving, source code changing, in those cases, in those releases, you will see greater advantage because you're producing a lot of new errors. In those cases, we found the clustering algorithms to perform better than the stable releases. And like we mentioned, unsupervised learning without any accurate model, because we can't have an accurate model because your source code changes, your customer data and customer input is changing, your errors keep changing. So it almost is impossible for us to have a perfect model. Some of the future work that we've planned for this is figuring out how to best validate our unsupervised learning itself. Like I mentioned earlier in my talk about online processing using Spark streaming. And then event-based error detection on live production clusters. So one of the uses that customers have come back and told us is that if you can put it in our live clusters and tell us why there is an error, when it occurred, that is going to be a big deal. So we plan to export all our repository and seed it into customer clusters and see how it goes from there. And the last point is almost the same correlation with other log events and customer use cases. So your matrices, which comes from system matrices, older logs, and newer exceptions. We want to triangulate all of these and then point to RCAs. That's pretty much it. I have no more time. I don't even know if I have left time for questions. Sure. Please go ahead.
I think you said that you installed 700 clusters
Mm-hmm.
tonight. Is that from a
So we have both. We have our own Yarn cloud, which is faster, OpenStack, which is not so fast. OpenStack, for you to install all the components that you want to install and then test, in some cases it even takes up to about 10 minutes. Whereas the Yarn cloud ones, because you're building it from a pre-baked image, that is faster. Not sure, but I can introduce you to the team here. Varun and all those guys are right here. I don't know if we've open sourced it yet. I don't think the code has gone out in the community. Not yet. Okay. All right. Thanks, everybody.